Okay, everyone, welcome back to your Company 30 tutorials. I'm recording a series of videos because I wasn't able to give the tutorial in person. So there's going to be different videos about different topics that are sort of covered in the assignment, and so should help you complete the assignment. In this video, we'll be focusing on context-free grammars, or I would say like this will be like an intro to context-free grammars and context-free languages. Okay, let me just give you a quick recap of what's been going on in terms of context-free grammars and context-free languages. So the way we started this class, and the way most theory of computation classes start is they start with automata theory, but in particular with describing language acceptors as models of computation, right? Um, we were looking at language acceptors, right? So language acceptors being um, computational models, right? Models of computation. So there's some kind of simulation of computation of sort of step-by-step computations, where for language acceptors, you give the language acceptor, let's call it M, some string, and M either tells you yes, meaning that M accepts the string, and so it should be in the language accepted by M, or it tells you no, right? It rejects the string and it says no, the string is not recognized by my sort of rules of accepting. Okay, so we've seen many language acceptors. We've seen DFAs, NFAs, NFA with epsilon A's, and we've recently seen non-deterministic and deterministic PDAs. Okay. Um, and so this is sort of one spectrum of the way to model computation. And it's the most natural because when you look at a transition function and we look at state transition diagrams, it's very clear that this machine is sort of capturing some form of computation, right? It's very natural for a computer scientist to look at an NFA or a DFA and say, yeah, I can kind of see how this would be an extremely simple computer that could carry out some very limited operations, right? Um, and I would say in terms of like regular expressions are quite models of computation, but I would just say regular expressions are very special because regular languages are very special. Because you can think of regular expressions as sort of the way of pinpointing exactly, of describing very succinctly a regular language. So I think of regular expressions as more like, you have the sea of regular expressions and the sea of regular languages. And then one regular expression points out a particular um, regular language, and it does so typically in a more or less compact way. I mean, um, from your assignment one and the conversion algorithm, right? That sometimes regular expressions can turn out to be very icky and not very compact. Um, but for simple enough languages, you have much more compact representations than if you were to sort of describe the rules of acceptance. Um, so regular expressions, kind of like uh, the another side of the same coin in terms of language acceptors. It's just that they're more sort of compact representations. Um, and then we have this sort of very different um, type of material in the theory of computation sort of course, and in several theoretical CS classes, this is often presented more or less in the middle. And those are I would what I would sort of generally describe as language generators. Okay. So language generators, they don't just have to be context-free grammars. Grammars in general are language generators. Enumerators are also a different type of language generator. Um, but really, you can just think of having some kind of system. Um, it could be some grammar G, can be some grammar G. And this grammar or this language generation system, it just spits out a bunch of strings, right? And if you take the set of all the strings that are generated by the generator G, then that's the language generated by the generator, okay? Um, and so that's where grammars fall under. So grammars are language generators, and so are enumerators. So enumerators are actually equivalent in computational power to Turing machines. And so you might see this later in the course. Okay, but we're going to focus on grammars and in particular on context-free grammars. Now, why is it important to have yet another sort of tool to represent languages? Um, this is mostly because grammars are very special in that um, they allow to model the recursive nature of non-regular languages, or just of languages. I would just say actually that's not a good definition of languages. Okay, so I would actually describe this, or I would sort of compare this. If you're asking, why should we study both of these things? I would sort of compare this to very roughly to saying that automata and the different automaton that we've seen so far, those are kind of like approximately like iterative procedures. So I would describe these as sort of iterative procedures, right? So you sort of provide the explicit steps. So you provide the explicit steps for accepting. Whereas grammars, I would say they're much closer in nature to recursive procedures. So procedures that use recursion, okay? Um, and it's more like they establish the rules of the language. So they establish the rules of the language, okay? So essentially they say, what are the rules that allow you to generate all the possible strings in this language? And so they heavily, these rules, they heavily rely on recursion. And so we'll see an example of that in a second. Um, and so you can sort of see this as an advantage because if there's a very clear way to describe how you would accept strings in a language, then that's telling you there's probably a really easy way of sort of creating the FA or the PDA. But in other cases, it might be super easy to say, well, all the strings in this language look like this, where you sort of have a base case and a recursive case. And that's very much more something that a grammar and we'll see a context grammar can do instead of like an automaton. Okay, so let's look at an example to make things a bit more concrete. So let's consider the following context-free grammar G, which generates the language L, which is AN B2N, okay, where N is a set of natural numbers. You know what, just to make this unambiguous, starting from 0, okay. Um, okay, so this is the sort of first context-free grammar we're going to consider. So how are we going to do this? Well, I'm going to sort of give you first the intuition of what I mean by describing the recursive nature of languages. Um, so what I mean by here is, what's the base case of a string being an L, right? So what's the sort of simplest string that you can think of that could be an L? Well, that would just be if you set n to 0, right? Because if you set n to 0, if you set n to 0, then you just get the empty string, right? So that's the empty string. So now, the recursive case would be something like, suppose you have a string, right? Suppose you have a string that's in the language L, right? Now, what um, does a slightly larger string look like by where you have to sort of use that string that you started with? Okay, so um, the recursive case is, I know that a n b to n is in the language L, right? Um, so how do I get a slightly larger string from a n b to n? Well, in this case, right, in this case, I just add an a to the left and I add two b's to the right? So in other words, if I have some string w that's in L, then the recursive case is add an a to the left and add two b's to the right, okay? So then I know that W is an L, so I know that it looks like A n B 2 n. And then if I add an A to the left, then I get A n plus 1. And if I add two B's to the right, then I get B 2n plus 2. But that's just 2 times 2n plus 1, right? And so that's the recursive case, right? So the recursive case is, assume that you have some string already in L. How can you build up a new string that will also be in L? That's the sort of general principle, okay? And so how does the context-free grammar allow us to very succinctly capture this kind of rule of the language L? So let's design, or let me show you that grammar. So just a reminder, grammars in general are four tuples. So they contain the starting variable s, a set of variables v, a set of terminals t, and a set of production rules p. Okay. So in this case, my set of variables is just going to be s itself. Okay. And my set of terminals, so terminals are just the letters that allow me to create sort of strings that will be in the language. Those are typically, the terminals are typically just the alphabet of the language, right? So this is just going to be AB, okay? And then P is where you actually get the bulk of the sort of work in your context-free grammar, right? Much like the transition function. So P, right, is going to contain production rules. And the production rules sort of map almost directly to the base case and the recursive case I just described. So imagine that the variable s, right? Imagine the variable s is something like you start at this variable, and at the end of a process of derivation rules, you get to a string in L. Well, what's the most sort of fundamental or basic case you need to get a string in L? Well, you need that S gives you, right, sort of leads you to the string uh, epsilon, right, the empty string, right? And so this directly corresponds to the base case, right? This just means that um, S gives you the empty string. The empty string is sort of a string of only that does not contain any variables, right? So it's sort of a string of terminals. Um, and so that's generated by my grammar, and it's going to be in the language generated by my grammar. Okay. And really what I'm just trying to say is it's sort of the sort of base string that's generated by my grammar. Okay, so then how are we going to do the recursive case? So my context-free grammar, it's always going to have a single variable on the left-hand side, and then really whatever you want on the right-hand side. Okay. So, well, let's think of the recursive case, right? The recursive case says that I start, like imagine I have some string in the language L. So imagine that S had already generated, right? S had already generated some string W in L. Now, how can I create an even larger string? Well, I have to attach an A to the left, right? And two B's to the right. Okay. So this is going to be my recursive case. And the way we can see this in action is, I start with the start variable S, and I use this production rule here, right? So I say I replace S with ASBB. And then again, I take this S and I use this production rule to replace it with. Okay, so I take S and I replace it with ASBB. So I have ASBB. Okay. And then let's say I stop. So I say, okay, I'm going to stop using this production rule. Now I'm going to use this one instead. So I replace S with the empty string. Okay, so I get A2, B4. Okay, and that's the string of terminals that is generated by this derivation, right? And so you can notice how this intuition of recursive of the recursive case sort of occurred. You can kind of see that from S, you were able to derive ASBB, and then that allow you to derive A epsilon BB, right? So that sort of tells you that S gave you ABB, so some string in L, and then you just created a slightly larger string by using the recursive case, right? And so that's kind of what we mean by capturing the recursive nature of the language. You're sort of just writing that in terms of production rules, right? And so if you consider all of the strings that can be derived starting from the start variable S, then that set is the language generated by the grammar G. So L of G is the set of strings of terminals for which you start at the start variable S, and using any number of derivation steps, you get to that string of terminal W. If you can do that, right, if from S you can get to a string of terminals W, then that W is going to be an L of G, right? And so here it's not too hard to see that L of G is indeed going to be L, right? So it's indeed going to be this AN B2N. I can just show you the first few generations in sort of terms of number of derivation steps of G. So S gives you the empty string, that's the first one. Then this would be the second one, right? I would replace S with epsilon on the sort of second derivation. So I get ABB, and then you can see this will give me A2B4, and then this next one will give me A3B6, right? And so on, right? And so I'll get in general, I'll get S gives me AN B2N. Okay? So I would say in general that the trick that I'm trying to teach you in this case is to sort of think of variables in terms of their role, right? So their role in generating strings. So very similar to how we sort of thought of, we said, okay, imagine this state in a DFA has this role. Now, if it reads an A, where should it go? And if it reads a B, where should it go? It's very much the same idea, except that here we're sort of dealing with generations of strings and with variables in production rules. So in terms of the role in generating strings, right? So this usually helps for the recursive cases. Okay. Okay. So I think that's all I wanted to say in terms of like introductions to context-free grammars and context-free languages. So um, in the next videos, I'll just do a few more examples of sort of designing context-free grammars that uh, generate languages. Um, and I'll also show you I'll sketch out how you're supposed to prove the correctness of a grammar. All right. See you next time.